Okay, myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri Srinivasa College of Engineering and Technology. Today, I'll be going to talk about optimizer, which is a most important topic in deep learning because it tries to minimize the loss function. If you look at the diagram, that is a loss versus model parameter, that is weight, and the initial weight is going to be here, and when you apply the gradient descent method, and it is going to be, which will reduce the loss function. Okay, and this is the point where you get the global minimum, and most of the optimizers are first order optimizers which are derived from the gradient descent. So there are other optimizers there which are not gradient descent. That is, for example, I can say um, genetic algorithm based. Okay, there where we use such the best solutions. Here we use gradient descent approach. So gradient approach is basically a first order iterative method. So this is a way we are going to look at today. And optimizer, as I said, optimizers are from the gradient descent. And in this category, we can have the whole batch is gradient descent, and here stochastic gradient descent, and another one is mini batch gradient descent. In the batch gradient descent, we use all data sets. When the entire data set will be used for the gradient descent approach. Here, stochastic, the name itself, I can say it is randomly that will pick the data, and the iteration will happen over there. And in mini batch set, instead of whole batch, we go by 32, 64, 128. This is a small batch will be used for the gradient descent approach. And most of the advanced optimizers that we use today, they're all based on the mini batch approach. Okay. The gradient descent approach, which can be enhanced with the help of momentum or adaptive. Okay. The momentum is basically it tries to have the past data, and adaptive is basically where we use the learning rate may be updated automatically, where the learning rate will be updated automatically in adaptive gradient descent methods. Okay, so here everything is going to be fixed, but in this case it is going to be updated. Okay, that we are going to see in the forthcoming slides. Okay. And when you combine the momentum and root mean square propagation, and we'll have a new optimizer, that is the Adam optimizer. This optimizer is widely used for the real-time applications. So basically, in gradient descent approach, that will reduce the cost function by changing the parameters weighted by us. This is a plot, 2D plot, and this is basically a contour plot. All that, as I said, in batch gradient descent, all the points are taken for the iteration, and we apply the loss function. We apply the loss function here over here to update the weights. Okay, so what is happening here? Here we consider all the data points. Whereas in stochastic gradient descent, we consider only one data point, okay, in each iteration, it will be randomly selected, okay. And what is happening? There will be a noise over there. When you look at the counter plot, there will be a noise over there. This is a point, I can say it is a global minimum, okay. This is a point where we get the global minimum, okay. And in case of mini batch gradient descent method, we take a small batch, okay, for consideration of each iteration, and we update the weights. Okay, so the advantages there will be advantages and disadvantages of each methods. And when you go for the batch gradient descent approach, and we'll have a slow conversion because of all the data points are considered for the iteration. So it is going to be slow convergence, and it is stable, but the conversion will be faster for the small data set, whereas for the large data set it is going to be very slow. Okay. And in case of stochastic gradient descent method, it considers only one point in that. So that as a result, it fast conversion, but it will have a noisy oscillation around the minima. Okay, so that is a disadvantage of this. So when we go for instead of single point, instead of considering single point, either single point or the whole batch, we can consider a small set of small batch, which will have both advantages and disadvantages of both the methods in the case of mini batch. Okay, so here we use 34, 64 each batch is going to be used in the mini batch gradient descent. So what is happening? It balances both speed and stability in this case. Okay. So where we get stability, here it is going to be faster. So we can have both. It will this mini batch gradient descent will have both advantages. As we said in the gradient descent method and the mini batch gradient descent method, we will have noisy things will be then the while updating the weights. Okay, so we'll have a noisy one, and we wanted to smoothen it by using a momentum based optimizations. So the gradient descent will be enhanced with the help of momentum. Okay, so what is happening here? We consider here the past history. Okay, so that's the way it works. And this if you look at this left hand side of diagram, this one is basically our whatever we have used in the case of gradient descent method, where we see a lot of noise out there to reach the before reaching the minimum point. So whereas in momentum based, it is smooth convergence will be that the you'll have a smooth convergence to reach the minimum global minimum. Okay, so what we are doing here is that we are updating. We use that momentum coefficient that varies from 0 to 1, and this is v t minus 1. This is the previous table we consider over here. This is the velocity term over here. Then it will be added before going for the updates. Okay. So when you have the momentum one, and it doesn't care of a small bumps. Okay, if you look at this one, if you have a ball over here, because when while starting it gets accelerated, it gets momentum, and it doesn't care about the small bumps, and it reaches the global minima. Okay, so that is the advantage of momentum based optimization. Okay, so when we go for the momentum based optimization, as I said in the as I explained, using the ball based thing on the curve, and what will happen is that when you roll the ball and it will come over here, and this is the first position, it will come over here after updating the weights, and it will come over here, then suddenly it will go to the opposite the positive gradient. Okay, so instead of coming over here, it may jump over there. So it will not have a stable one. It may lead to oscillation before convergence. Okay, so that is a disadvantage of using the momentum one. Okay, so when we to avoid that, we use Nestro momentum. That is basically what it does is before before jumping into the next position, it will look at, okay, that is a point here. Okay, look ahead of positions before jumping over the fourth point. It will consider it will get and will be operated over there. In the case of momentum, the gradient will be operated where that particular point is, where the current position is. Here it is not the case. There is the current position, the gradient will be operated at the current position. Here the gradient will be operated at a lookout position. Okay, so that is the difference between this standard momentum and stability, which will try to reduce the oscillations. Here, if you look at this, this is a formula that we use. This is basically a learning rate, and the grade del J is basically the gradient of the loss function with respect to the weight. Okay, so this is the theta t is basically a current position. Here in this case, if you look at this, here we apply the lookout positions. Okay, so that is a network momentum will help us to reduce the oscillations. So before going to this, and we should understand the when we use in both cases, in both gradient descent and momentum, we use a single learning rate. Okay, so what is the advantage of using if you have a large learning rate, and if you have small learning rate? Okay, so this is a gradient descent approach. So this is a WT1 is the new weight, and this is the old one. and minus eta gt. Gt is basically your loss function. Okay, loss function with the gradient of the loss function with respect to weight. Okay. So when you have more GT, that is going to be your steep. The slope will be steep, and when you have a small GT, then it will be a small. It is going to be a gentle slope. Okay. So when you have the large learning rate, and what will happen? It will that grading term will blow up further, leading to the drastic weight updating. So because this is going to be large, this GT is going to be large, and then in this case, learning rate is also lost. Then learning rate is also large. So what will happen? Both the thing will get multiplied over here, and it will it will lead to the drastic weight updating. Okay. So what we have to do is when there is when GT is very small, if you have a large learning rate, then it tries to converge smoothly. Okay. And similarly, I can say when eta is very small, then when you have a steep slope, there will not be any issues. When you have a small slope, and when you have and learning rates are very small, and it won't update the weights. Okay. So basically, when you go for the updating the weights, and it depends on the learning rate and the gradient of the loss function. Okay, these two terms are very important in updating the new weight. Okay, so that is the purpose of using single learning rate. So instead of single learning rate, and people have started to work on adaptive learning rate. Okay. So with a single learning rate, you can't satisfy both the conditions. And adaptive learning rate, what is happening? It try to update the learning rate based on the previous updates. Okay, where we use in the momentum one, we look at the previous one. Similarly, here we update the learning rate based on the previous updates. Okay. So in adaptive rates, and what we do here is that we use this sum of square gradient. This is a sum of square gradient. Okay, and we use this learning rate can be adjusted based on this learning rate can be, this is going to be effective learning rate. This term I can say this is effective learning rate. This can be updated. This can be adjusted based on the VT. Okay. So when you have this is going to be small, but this update will be changed. So as a result, that the new update will change. New updated weight model parameter will change accordingly. So when you have the previous updates are very high, the learning rate will be decreased. Okay, when you have this VT time is more, what will happen? And your denominator is going to increase, and as a result, the effective learning rate will be decreased. Okay, so when you have the previous updates are very less, and what will happen? This time is going to be this time going to be the decrease, but not the great extent. So in order to avoid that, we use so sometimes VT may be 0. So in order to avoid such a situation, we add a small constant over here, that the amount is going to be 10 power minus 8. So this epsilon is added for the numerical stability. Okay. So when we go for many iterations, and what is happening, it accumulates this GT square, it accumulates the square gradient, which makes that vanishing gradient, which makes to vanish the learning rate. Okay, so that is a disadvantage of adaptive gradient. So what we have done here is that, and where in adaptive one we use sum of squares, and here we are using the moving average instead of sum of squares. Okay, so when you go for the moving average, and it will have a exponential factor will be there, because and each previous update will have a history over there. The older one will not have much importance, and the reason will have more influence in this case. So when you go for V0, V1, V2, and so on, and the older will not have much effect, but whereas the reason will have much influence over there. Okay, so basically this this function, this root mean square, basically this root mean square will have is calculated. I mean, this one is basically this one is basically works on the basis of moving average instead of full sum of squares. So this moving average will have a stable and adaptive learning rate. Okay. So then this avoids that vanishing learning rate. Okay, it prevents the learning rate from the shrinking too fast. Okay, that is the advantage. That is a disadvantage of Adagrad. And we have Adam optimizer. This is mostly used in most of the real world application, I can say. Okay, so well, as of now, it is mostly used. It combines that momentum and root mean square, because momentum will give a smooth conversion, and the RMS will have to avoid the RMS will avoid that vanishing learning rate. So it has some sort of bias correction as well. Okay, this particular Adam optimizers. So we have the two things on we have two momentum. One is MT, and another one is VT, and we have everything is, I mean, that for the MT is based on the average digging average gradient, because it works based on that. And when we look at second momentum, it is going to be used on this. It is going to be exponential factorial is involved in over there, and it is also based on moving average. Okay. So if you look at the first momentum, it accelerates the convergence along the consistent directions. In second one is adopts the learning rate per parameters that we have seen in the adaptive learning rate, Adagrad. Okay. So what we have done in the bias case, these are going to be the bias one. Okay, these are going to be the bias corrections. When you don't have a bias correction over that the early updates are going to be very small. Okay. So when you have the bias correction, then it reflects in the updates are going to be fast, and as a result, it works well for the real time applications. Okay. And the next one is Adam delta. The Adam delta is basically it doesn't have any, initially it doesn't have, you don't need to manually fix that learning rate. Okay. So if you look at the denominator, you have VT, and numerator you have UT minus 1, the square root of UT minus 1. So that in the denominator, and we have the recent gradients, and the numerator we have the recent updates. Okay. So this is going to be applied in the finding the new weights. Okay. This adaptive Adam delta doesn't, since it doesn't have fixes, it doesn't manually fixes the learning rate. Okay, it adjusts the weights. It adjusts the weights, and it doesn't require any predefined learning rate. Okay, so that is the advantage of Adam delta. Thank you. This is a summary of all optimizers, and first three one are gradient descent, which were enhanced by momentum and adaptives. And the conditions we use in the summary table is learning rate and momentum adaptive, whether it is of momentum or adaptives, and what is advantage and disadvantage, and why we have gone for the other categories. And here in this column is basically focus on sum of squares and moving average for the gradient updates. So with that, we wind up the session on optimizers.